Okay, good afternoon. Um, Hopefully you're finishing your homework. Um, so today's plan is to continue with the arithmetic circuits, which we had just started on last time. Um, so main thing we'll cover today really is to move into how we handle arithmetic with signed numbers. So that would be kind of main focus today. So towards the end last time, we had started looking at addition, but still sticking with positive integers represented in the normal base 2 format. And I had introduced two types of hardware modules, one which we called as a half adder, and that its purpose is to add 2 bits. And since when you add 2 bits, the output can, in general, would also need 2 bits because if both bits are 1, then the value of the output has to be 2, and therefore we need 2 bits to represent. So half adder does that. Half adder takes what? Oh, sorry. I forgot to connect. Okay, thanks. So we introduced half adder as a hardware module which takes 2 1-bit inputs and produce 2 1-bit outputs, one of which represents the sum. So that's the output in the same place, same bit position, and a carry which has a higher weight because it's going to add to the next higher place. So you can think of it as output S has a weight of 1 and output C carry out has a weight of 2. And then we talked about the concept of full adder, which deals with the fact that at an arbitrary bit position, you also have a carry coming in. So you're really adding 3 1-bit numbers, right? And if you add 3 1-bit numbers, the maximum output is 3. So you still need 2 bits in the output. So full adder, whose truth table is given out here, really takes 3 1-bit inputs and produce 2 1-bit outputs. And the 2 1-bit outputs correspond to sum and carry out. And the 3 1-bit inputs are A and B, which are from the current bit position, and then C in, which is the carry coming from the previous bit position. And there are a variety of ways we can build this thing. One is by just looking at the truth table. So you can look at that the carry out is 1 if either 2 or all 3 input bits are 1, right? So that's the majority function. Majority of the bits are 1, and we had seen that circuit before, like this. Or alternatively, okay. So the other thing is the sum bit, and the sum bit basically is going to be 1 if either one of the input bits is 1 or all 3 of them are 1, right? If 2 of them are 1, then 1 plus 1 will lead to 2, so we'll get a 0 in that bit position. So it's basically a function which is often referred to as odd parity. That is, we are looking for an odd number of ones, right? I mean, either there's 1 1 we define as the two inputs are not equal, right? I mean, it's either 0 1 or 1 0. When we talk about a 3-input XOR gate, there are a couple of different ways potentially you could define it. One way one could have defined it is that a 3-input XOR gate is one where the 3 bits are not equal. But that's not how we define it. We define a 3-input XOR gate as a gate which outputs 1 if an odd number of input bits are 1. Okay, so it's 3-input XOR gate. That's how it is defined, and that's what the symbol you see out here. So we get the sum bit and the carry out. So we could design this way. And the XOR gate itself, a 3-input XOR gate, you can actually design using 2 back-to-back XOR gates the way I had done at the end last time. So we could do it that way, or alternatively, we can approach it by using the half adder, which we already designed. So the half adder, the way to think about it is I have 3 bits to add up. So I'll first add 2 of them, let's say A and B, and that will tell me the sum at that position and a carry out from there. But I still have 1 more bit remaining. So I take the sum, which is coming out from the first half adder, I add it to C in, which is the 3rd bit which we have, and then we are going to get the true sum. And now I have 2 carries to worry about, and kind of the idea is if either one of those carries is 1, we get a carry out, so there is an OR gate associated with it. So you can convince yourself that it does the kind of the right thing. And we are in some senses, another way of looking at a full adder is we are counting how many ones are there, right? I mean, my output corresponds to how many ones are there. So it's a ones counter. Okay. So this circuit also achieves the full adder. Once we have a full adder, then we can create a n-bit adder with our bit slice strategy, or in software terms, kind of a loop. So I just stack these full adders. I take carry out from 1 bit to carry into the next bit. So that emulates the way we do addition normally, right? I mean, we add digits at the same place and the carry in coming in, we add all of it together and we get a carry out. And then for the least significant bit position, I could have used a half adder out here. This one could have been a half adder because I don't have a carry in coming into the least significant bit. But usually we design it so that we also put a full adder there, and then we tie its carry into 0. Now, later on, we will see that if I make carry in to be 1, then that can play a role in making this adder do some other stuff. Okay, like at the very least, I can implement a function called a plus b plus 1, for example. I can also use it to implement a plus 1 and tie b's to 0. So it's usually useful to use a full adder even in the least significant bit. Okay, this gives more flexibility. So we have this way of doing addition, and just by analogy with what we saw in arbiters and all, this one it has area which is proportional to n, it takes delay which is proportional to n. You might imagine again, I can add things perhaps faster by again creating a tree of some form, and indeed one could do that. So there are faster adders. This is kind of the most obvious way of doing n-bit addition, but we'll very soon see possibly some other ways of doing it too. So this is called ripple carry because kind of the idea is carry is rippling through. There's some other interesting things which happen if you think about it. As the carry, so let's imagine at t equal to 0, at time equal to 0, I present a and b to this adder. So what will happen is the most significant bit of the sum will at that point in time immediately add a and b at that bit and whatever was the value at the carry in, and it will put some output out here. But then later, as the carry ripples through, eventually after a delay which is proportional to after a delay propagating to the other bits, a new value of carry in will arrive out here. So if you were to observe what is happening at the some bits, they may jump up and down repeatedly before they settle in. And the reason is that this way the delay is pretty short, whereas this way the delay is very long. And that's a classic situation with our hazards that we had seen before, right? Because if the delays are different, then an output bit can jump up and down. So what you would see out here in an adder like this is S0 will settle very quickly, S1 a little bit later, S2 even a bit later, and Sn minus 1 and carry out will settle very late. And if you were to observe them, they can sort of fluctuate. So one has to be very careful that Just because Sn-1, if let's say you were to put an oscilloscope or some instrument out there, it may change and you'll say, aha, I have my new value. That may not be correct. Okay, you have to wait for the whole time. So that rippling effect, literally, you can see as the signal goes up and forth, back and forth, it creates hazards. It also, if you recall, I had mentioned that transitions of signals also can burn power needlessly, right? Because capacitors start, discharge. So ripple carry adder has lots of consequences, because if I change the input, then the output bits may change many times, as opposed to just once at most, right? That's ideally what we want. Okay.
Do you also call the arbiter version of this ripple carry? Do we see similar like rippling effect of this the values?
You would see the same rippling effect. Excellent question. We don't call it ripple carry because, but there is a rippling effect there indeed. Okay, we wouldn't call it ripple carry, but it's a ripple type design there. Absolutely, yeah. Great, good question. Yeah. So you see kind of this family of designs which we are seeing, right? I mean, which operate by, we think of our design as n bits, and we have a signal traversing from least significant bit to most significant bit or vice versa. And so this ripple carry adder is an example of that. And just to make sure you're comfortable with the notation, it's an n-bit adder, but the bits are listed as 0 through n-1. And carry in out here, if I'm just seeking to do a normal addition, I will tie it to logic 0. Okay, so since we create, like modern computers are in some cases 64-bit or even 128-bit computers, so we need often need to add numbers with many bits. And so this delay through the ripple carry adder can add up to a lot of delays. And of course, we want a full addition, not just a single addition. Sometimes we do multiplications and all, which involve many additions. So addition is pretty important and often can become a bottleneck for the speed of your computer. So there's a lot of effort which has gone on optimizing full adder. You want a design which uses few transistors, can be laid out on silicon in a compact manner, and has very low delay. So one of the problems that happens is the following. Remember this majority circuit that we had, right? Which kind of looks something like this. So what is happening is that's the bottleneck, right? Because carry in comes into the majority circuit and goes out, and then C out is generated out there. So the point to note is this delay is not so much of a bottleneck, because that's just going to the sum thing. The delay that we really care about is the delay which goes from carry, goes to carry out, goes to carry out here, goes, right? I mean, this is the ripple path. So our bottleneck is really the majority circuit, right? Because the sum part is just at that bit stage, it's not rippling through. So when we optimize this thing, we really seek to optimize that majority circuit. Now, one of the ways to modify this thing is, so this is if you were to kind of design this these things, what you see out here is a kind of a highly optimized full adder. It does the same thing that I'm showing previously, but in a much more optimized manner. If you see, this is the part which is doing the magic, right? Carry in to carry out. So the way kind of it has been structured is that we really minimize things on the ripple carry path and then do as much work off that path as possible. So delay of this part doesn't matter, because if I'm looking at, let's say, bit number 63, it has plenty of time to settle it. So I can make the delay out here pretty long if I so wish, and I can make the delay out here also quite long. Okay, it's the delay from carry in to carry out which truly matters, and a lot of effort goes into creating a circuit where that delay is short. Okay, and so here you kind of see these G's and P's listed out here, which I also had earlier. So a lot of people, one strategy for designing these these things, thinking about addition, is the following. If I examine A and B, then there are two possibilities. Just looking at A and B, I can say carry out is definitely 1. How can I say that? So what values of A and B will guarantee that carry out is 1, irrespective of CN? When they're both 1, right? So if I see at a bit position, I see A and B are both 1, I don't need to wait for C in, right? I can immediately say C out is 1. So that is referred to as generate. Okay, I'm generating a carry. And statistically, if your numbers are coming reasonably randomly, I can benefit from that, right? I mean, if bit number 54, A and B are both 1, I don't need to wait for that ripple coming in. I can immediately start there, right? So that's one point to note. Another thing is, I can, looking at these bits, I can also say, do I need to propagate the carry? That is, so carry certainly 1, carry certainly 0. That would be A and B are both 0. But if A and B are either 0, 1 or 1, 0, then I will propagate what is coming in. If carry in is 0, then my carry out will be 0. If carry in is 1, carry out is 1. So usually these circuits get organized this way, that I look at A and B, and then I compute 2 intermediate values, propagate and generate. Generate means carry out is definitely 1, and propagate says if propagate is 1, then carry in C out will be equal to C in. Okay, and if both P and D are 0, then again I'm done. So that's what these P and Gs, we'll see a little bit later more, but we kind of think of the addition in terms of these propagate and generate to begin to optimize circuit. So can I do better? Can I do better than order and delay? Right? I mean, we saw order and delay, and one thing you can so one strategy, perhaps I already alluded to, is that yes, I can take advantage of, if I know I'm generating, then I can proceed from there, and statistically, unless my numbers I'm adding are biased in some manner, quite possibly I can do better than having to ripple all the way through. But there's another strategy that we can do. So let's say, so in computing, it's the strategy of what is often called as pre-computing. So let's say I have to compute to a function f. And if I know input x can take one of 2 values, either x is 100 or x is 200, then and that's the only 2 possible things. So one possibility is I wait until x arrives and then compute f of x, and the other is I can pre-compute f of 100 and f of 200, and then when x arrives, I just select between the 2 pre-computed outputs, right? So pre-computation is something we use in software a lot. That's caching of results, basically. So I can do something like that out here. So we'll see shortly a design which is based around that concept. So what this slide is basically saying is that if I am sitting at a bit, carry in, which is coming in, can only have one of 2 values. It's either 0 or 1, right? So I can compute the result assuming it was 0, and I can compute the result assuming it was 1, and then select between the 2. And we'll make use of that fact. So this pre-computation is basically the strategy we will use. So this is what we will do. We will create this. So let's imagine I take our n-bit adder and I divide it into chunks. And I'm going to look at a 4-bit chunk. And what I do is I add these 2 4-bit chunks. So let's say AI plus 1, AI plus 2, AI plus 3, and likewise BI plus 1, BI plus 2, BI plus 3. I add them up. Okay. Or in this case, A0 through A3. So I kind of add them up, and I'm going to get some result. Except what I do is I compute the results both assuming carry in was 0 and carry in was 1. I do two additions. Okay, so I use two 4-bit ripple carry adders, one where I make C in to be 0 and the other where I make C in to be 1. And then later on, at some point in time, I know the true C in. And then using a multiplexer, 2-to-1 multiplexer, I can select results from one of the two chains, right? If C in was 0, I will select the results from the upper ripple carry adder. And if C in was 1, I will select the results from the lower ripple carry adder. And I can do it for the sum bits and I can do it for the carry out bits. Okay, so again, sort of just imagine a 4-bit chunk somewhere in my adder, and I kind of compute from the lower bits. C in can just take one of these two values. I add these two 4 bits, assuming C in was 0 and assuming C in was 1. And then when I actually get the C in, I select the right result. And then what we can do is a game like the following. So let's say I'm performing a 16-bit addition. So the first 4-bit, of course, I have the C in. C in is probably 0, let's say. So I just compute it. I get my result. But for the next 4 bits, what I do is I don't wait for the C out from this C out. What I do is I go ahead and optimistically compute, assuming this C out was 0 and 1. So I have two 4-bit adders. And I do the same thing for the next 4 bits, and I do the same thing for the next 4 bits. And then what will happen is after rippling through the first 4 bits, C in will arrive. But by this time, these guys have already computed the result. So very quickly, just through the mux delay, I'm going to get the next result. And then meanwhile, by the time this guy comes, again, this part has done its job. I can just again select and same game out here. So now intuitively, with a design like this, instead of 16 bits worth of delay, I will have 4 bits of delay out here plus 3 selection delays. And let's say, hand wavily, let's say selection delay is equivalent to a bit delay. Okay, let's say. So that means instead of 16, a delay of 16, I have a delay of 4 plus 1 plus 1, 7. So I've improved the design by some factor in speed. Of course, there is a cost. I'm paying for more adders and also the multiplexers, right? So I'm doing this trade-off between area and time. In general, this is a trade-off that you will see in hardware. If you're willing to throw more gates, then you can get up with a faster design. So more area, more power, but faster. It's usually a good trade-off because oftentimes squeezing some additional transistors is pretty easy. I have made a point earlier also, which is nowadays wires are the more costly thing, transistors are not so. So I could probably play this game relatively easily without as much cost as one might think. Okay, so a 16-bit adder, which I divide into 4 chunks of 4 and play this game that upper chunks pre-compute the result, assuming both possibilities of input or carry in coming in to them, and then we just select. Now, can we do better? Anyone? Can I adapt this strategy to do even better in terms of delay? Can you speak louder? Not sure. Maybe you are alluding to the right direction, but I am not so sure. Let's think about this design a little bit, right? I mean, let's look at the upper 3 blocks. When will their result be ready? The 2 results. assuming C in is 0, C is 1, after 4 units delay, right? So at t equal to 4, let's say each full adder takes 1 time unit, right? So at t equal to 4, this guy is ready, this guy is ready, this guy is ready, this guy is ready, right? And then at t equal to 4, the selection arrives, it selects the result. This guy is ready at t equal to 5, the one which the next stage is C. Right? But that means that this guy, which sort of used 4 bits, it's sitting idle for 1 time unit, right? Because it became ready at t equal to 4, but its C in is coming at t equal to 5. So what can we do? Exactly, right? So I don't have to do 4 full adders here. I can do 5 full adders. And again, I play the same game. Next stage, let's say I was adding a bigger number, right? So I can have even more full adders out there. So kind of the idea is we grow the size of these blocks as we move towards the higher bits so that hardware doesn't sit idle. Okay, because idle, again, cost. So that's actually another principle in hardware. Hardware which is sitting idle is not doing anyone any good. So you should design your system so that at all times, all hardware is kept busy. And that's kind of, again, sort of a good rule of design. Anything which is idle is wasted area, wasted power. So, but in this context, what it means is that instead of a uniform blocks of 4, I will have smaller block at the beginning, then a bigger and bigger and bigger. We can play that kind of a game. So, yeah. So this is a design which seeks to do that. So what's happening out here is, in this case, the first stage is 2 bits. Next stage is also 2 bits, so that they meet in time together. By the time the second stage has done its 2 bits, the first stage has its carry out ready, and so it can just do the selection. Next one is 3 bits, because the delay through the bottom one is going to take 2 bits plus a multiplexer, and again, hand wavery, let's say a multiplexer takes 1 unit delay. So, and then the next stage is 4, and next stage is 5. So in this strategy, we keep increasing the block size by 1 bit. Okay, and that would be kind of your optimum design in some way. This is assuming multiplexer takes the same delay as a full adder, and which is probably roughly speaking true. Okay, so this non-uniform block size can help, and if you kind of work out the strategy, this thing, its delay instead of order n is order square root n. Okay, so it grows more slowly, right? Square root function is a slower function. So that's kind of the idea, that I'm sort of throwing in, of course, I have roughly twice the number of full adders, right? I mean, there's a tiny bit discrepancy at the bottom, but roughly twice the number of full adders, and I need these multiplexers, and you can roughly, a multiplexer a bit cheaper than full adders. Okay, so on a per bit basis, so you can think in terms of these costs, but it's usually a good trade-off. So this kind of design is referred to as a carry select adder. Okay, because I'm pre-computing and then selecting between the two. Okay, that's the strategy. This notion of pre-computing and selecting, yeah, there are many terms in computing, right? I mean, it's pre-computing is often also referred to as late binding, but kind of the concept basically being, I just attempt to hide the delay. Okay, and so that's what's going on. You can apply it to other type of hardware also, but in this case, it's being applied to full adders, to addition. So so you should be able to kind of, given, if I were to tell you what the delay of full adder is and the delay of a multiplexer is, then one should be able to design the optimal carry select adder, how many bits I'm going to put. In this case, I assumed that multiplexer delay is the same as a full adder delay, but it doesn't have to be. So Someone can do these kind of optimizations. But this is the big win. I mean, think about it this way. If I am designing a 64-bit adder, right? So instead of 64 unit delay, right? 64 bits, square root of 64, 8. That's a huge improvement, right? So this can yield big wins. Okay. So carry select with non-uniform design kind of is a good strategy. And I think for most kind of number of bits that one typically encounters, something like this is enough. If all your goal is just sort of adding 2 n-bit number, where n is the typical number of bits in the computer, which nowadays is 64, right? But that's not where adders end, unfortunately. Sometimes I need to do multiple additions in a single instruction. Okay. Multiplier is an example, right? If you're multiplying two numbers, you are doing lots and lots of additions. Okay. So we need even faster adders. Okay. Simply because we are doing lots of additions. Then there are examples where we are adding very large numbers, not just limited to number of bits in the computer, but arbitrarily long number of bits. There are scientific applications where maybe dealing with very large numbers. Cryptography is like that, kind of routinely deals with large number of bits and adding them together, like thousands of numbers which are thousands of bits long. Okay, so there is an even faster design, and this one is a little bit more complicated. So bear with me as I attempt to explain it. It's called carry look ahead design, and this is where we make use of that propagate and generate, which I mentioned a little bit earlier, which is there we were saying I can look at a bit and say, will it generate a carry or will it propagate a carry? Okay, so we'll generalize that concept out here. So carry look ahead adders, they give us order log n, you'll see. Now log n is even slower growing than square root of n, right? So it's log to the base 2n. Okay, if you want to it truly, but it doesn't really matter. It's log n. Okay, so it grows much slowly. So for large n, large number of bits, carry look ahead adder wins handedly. Okay, but for modest bit sizes, 64 and all, carry select will probably win out. So basic idea is builds upon that generate and propagate that I mentioned. So let's look at one bit, right? Again, so at single bit level, I have 3 inputs, A, B, and the C in, and normally I have 2 outputs, right? Carry out and the sum. But instead of doing that, I'm going to first compute. So this is normally what we do, okay? But we are going to think of it a little bit differently. What we are going to do is we are going to create this propagate and generate, and then we are going to express carry out in terms of those propagate and generate. Okay, sum we can do the standard way. Sum is just this part. Okay, so sum is the standard, but we are going to rethink how we are doing carry out. So what's propagate? Remember, propagate was that I carry out is equal to carry in. What is that condition? Okay, and that condition was that A is 1, B is 0, or B is 1, A is 0. So that is XOR. So that's the propagate. But very commonly in these designs, we kind of say, if both A and B are 1, then I'm generating, but effectively I'm also generation with override. So very commonly we use propagate as a plain A or B as opposed to A XOR B. What's the advantage of A or B, the first expression versus the second expression? Yeah, it's a lot less expensive. If you think about XOR, it actually requires 2 stages of logic, right? You have to, so XOR requires has a more delay, whereas OR or NOR, these kind of functions can be implemented more cheaply, fewer gates and all. So usually propagate is done the first way. Generate means I'm generating a carry, irrespective of whatever is coming in, and that corresponds to both of them being 1. Now let's think about what the carry output would be. Carry output will be 1 if I'm either generating a carry, right? So that's the generate part, or I'm propagating and incoming carry is high, right? So generate means irrespective of carry in, out, my carry out is 1. Propagate means if propagate is high, then I'm going to propagate the incoming carry. So with this definition, I can say carry out is 1, that is Ci plus 1, right? Carry out from position I. Carry out is 1 if I'm generating, that's the G, or I'm propagating and incoming is 1. So instead of doing this majority function, we can rewrite carry out in this term. Carry out from any bit is generate or propagate and input incoming is 1. So this is just a reformulation. We haven't come to the carry look ahead part, but you'll see that it plays a very important role. We are going to create kind of a structure around this. So for a given bit, or even for a set of bits, right, a block of bits, I can basically define this generate and propagate, and that's what we are going to play with. So let's see how carry look ahead works. So again, much like carry select, we first examine a block of bits. So I have a block of bits. Let's consider bit number 0, 1, 2, 3 within that block. Okay. And then my full adder gives out the sum at each bit position. So that's just the XOR part of it. So given A0 and B0, I get S0. Given A1 and B1, I get S1, and so on and so forth. And the corresponding carry, right? So carry is coming in. But from this full adder, now I have this full adder which gives propagate and generate. It doesn't give me the carry out. It gives the propagate and generate. Now I have this purple block, which is referred to as a 4-bit carry look ahead block. It's a sum logic, and what is happening out here is it's receiving propagate and generate from each one of the 4 bits that we have out here. Okay, so it's receiving it from bit 0, bit 1, bit 2, bit 3. Now so propagate and generate can be computed by the blue blocks in parallel, right? Because they don't, propagate and generate do not depend on carry in. They only depend on A and B at that bit position. So very crucially then, all these signals can be computed in parallel in the same amount of time without waiting for any carry to ripple through. The rippling part through this 4 thing is handled by the purple block. So the idea behind purple block is that now for this whole group of 4, we are going to generate, we are going to output a propagate and a generate, whose meaning would be, does this 4-bit block, will it generate output, carry output, or will it propagate a carry output? So this notion of propagate and generate, I can examine at the level of the 4-bit block. I can say, does this 4-bit block always output a carry for the next block, or will it propagate, right? So generate and propagate are concepts I can apply to groups of bits too, right? Does this group of bit create a carry, or does it propagate a carry? So this group of 4 is receiving a carry in, right? And which will go to the blue block and the purple block. But the job of the purple block is that based upon the propagate and generate, it is going to generate, it's going to output, propagate and generate for the whole block. So the meaning of PG is this block of 4 propagates the incoming carry. And the meaning of GG is that this group of 4 is going to generate a carry. So G stands for group. PG is propagate for the group. GG is generate for the group. So what this was my original equation at individual bit level, right? At individual bit level, I could define carry out based upon propagate and generate. So that part I can still do, but I need to find equations for PG and GG. How do I define generate for the whole group and propagate for the whole group? So intuitively, let's again reason. Generate at the bit level means that bit is generating a carry. Propagate at the bit level means that bit position is propagating the carry, right? So what about the group? When will the group generate the carry? Well, think of it this way. It will generate the carry if bit 3 generates the carry, right? That's case 1. Or alternatively, bit 3 propagates the carry and bit 2 generates the carry, because if bit 2 generates the carry and bit 3 propagates it, then again the whole group will generate. Or bit 3 and bit 2 propagate and bit 2 generates. And then finally bit 3, 2, and 1 propagate and bit 1 generates, right? So there are 4 ways this group can generate a carry, right? The most significant bit generates, the next one generates, and the left of it propagates, and so on and so forth. So that gives us the equation intuitively. Let's see. Yeah, here. So group generate is saying that group G3, bit 3 generates, or bit 2 generates and bit 3 propagates, or bit 1 generates and 3 and 2 propagate, and so on and so forth. So this is the group generate. I can create a generate signal for the whole group. And propagate for the whole group is simple. Propagate for the whole group is if everyone propagates, right? If that has to be true. Every bit has to propagate. If that is true, then the incoming C0 will get out, will come out at C4. Yeah. Your question?
So is C1, C2, and C3 in that diagram? Would that be what the 1-bit pull out here before C outs?
C1, C2, C4 are the carry in to the bit number 1, 2, 3, and C4 is really the group carry, the output from the whole group. Oh, the next another 4-bit block. Okay, so we'll see that later when we stitch it together, but just imagine that C0 is coming from someplace. Okay, something which is to the right of us providing this. Okay, so C0 is carry out coming from a lower bit or a lower group, and my job out here is that for this group of 4, I want to generate carry out, which is C4. I want to generate signals PG and GG, which tells that does this group as a whole generate or propagate. And then, of course, internally I have to compute S0, S1, S2, S3, but computing these requires C1, C2, C3. So if you see that these signals C1, C2, C3 are being fed back to the blue blocks. Okay, so that is just the original definitions, bit level definitions. So for example, what is C2? Well, C2 is if let's look out here. So C2 is if so C2 is carry going into bit 2, and so C2 will be high if bit 1 generates a carry, so that's G1, or bit 1 propagates the carry and bit 1's incoming carry was 1. So that's the equation out here. So this expression that you see, all of this is also being done in the purple block. So purple block is doing sort of 2 things, right? Firstly, it's computing C1, C2, C3, and C4. C4 is a carry out. and it's also generating and it's also generating this PG and GG. CG is the same thing as C4. Okay, so it's the output from the whole group. So what I've now done is I've generalized the definition of, like, instead of saying full adder, which is 1 bit, I've now said I have a group which adds 4 bits. It takes 2 4-bit numbers, produces a 4-bit sum. It has a carry in, it has a carry out, and it has this group propagate and group generate.
What if they all,
Yeah.
like, what if every single bit?
Oh, with if everything generates, right? So what will happen out here is everything generates. I know C4 immediately because C4 is just the generate signal. C4 is the carry out from bit number 3 out here, and so if bit number 3 is generating, I know immediately C4 is generating. C4 is. It doesn't matter in that case what's behind. So which is why you see out here GG. Well, okay, so let's look at C4 or CG. So it's saying this is C4 is high if the group generates or the group propagates, and C in, which was C0, was true. Okay, and for group generate, I can say the group is generating if bit 3 was generating, or bit 3 was propagating and bit 2 was generating, or, and kind of that argument goes on. Okay, so it's almost like whatever bit position I'm in, if I'm in the middle of the group, then if I am generating and everyone higher than me is propagating, then the group will output a 1. Okay, so that's kind of the intuitive stuff which is happening out here. But what we have accomplished this way is that now I have a 4-bit group, which is kind of like our full adder, except now for 4 bits. And it has all those properties. It adds 2 4-bit numbers, it generates a carry, it generates a propagate, it generates a generate. And now, given this, I can generalize it. Why stop at 4-bit? I can create an 8-bit thing. How will you create an 8-bit group? Well, let's think about it, right? So 8-bit group is going to generate a carry. So it will have to go to, sorry, 4-bit. So I can think of the 8-bit group as 2 4-bit groups. The lower 4-bit group is going to output a carry, which will go into the next 8-bit group. So that part is easy, but I also need to do a generate and propagate for the 8-bit group. So let's say I've given you this whole design, right? 4-bit, which outputs propagate and generate. And you have 2 of these, so you stack them together, and I'm asking, what's the generate signal for the 8-bit group, right? 2 groups of 4. What do you think it would be? When would that group of 8 generate a carry? Given that I already know when the 2 4 ones are generating and propagating. Anyone will take a stab at that? So very similar logic, right? So I have 4-bit group, another 4-bit group, right? Each one of them is giving a group generate and a group propagate. If I look at the whole thing together, what do you think, under what condition this, and this is feeding like this, right? Under what condition will this group of 8 generate a carry? When its generate would be high. Excellent. So let's call it GGH, GPH, GGL, GPL. Then for the whole group, I would say if GGH is high and, or GPH is high and GGL is high, in that case, the whole group will generate. And the whole group with similar manner will propagate if both propagate. So I can begin to stack these groups to create ever larger groups with this generate and propagate strategy. And that's kind of the idea. So I can take 4 of these. I can now create a group of 16. I can take 4 groups of 16 and create a group of 64, and so on and so forth. So this kind of logic out here. And if you see, we are creating a tree out here now. Okay, so we kind of start with individual full adders, which have propagate and generate. I form groups of 4. The group of 4 has propagate generate. I take 4 groups of 4. I create a group of 16. I take 4 groups of 16. I can then create a group of 64, and so on and so forth. So much like when you do binary tree search and all in software, it's kind of the counterpart out here. I'm kind of dividing things into this hierarchical tree in order to get a delay which is much faster. Anytime you have a tree-like structure, your depth of the tree basically increases as logarithmically, and which is why this thing has a delay of log n. Okay. So for example, a 16-bit CLA takes 8 gate delays versus 16-bit triple carry takes 47 gate delays. So much faster designs emerge out of this. So if you are using modern processors, they have basically carry look ahead adder. Okay, highly optimized using this kind of a strategy, because the reason is we do lots of additions. Okay, and even though they take more area, because we are now introducing this look ahead circuitry to play this game of G and P, so additional logic, but it's worth it because we win out, and particularly as our computers are getting like make use of more bits. I mean, small microcontrollers in the past used to be 8-bit, triple carry was fine. Then we went to 16 and 32 and 64, and now in some cases 128. So we need to do addition fast. So that's carry look ahead adder. It's a more complicated design, hard to grasp. So ask TAs questions, very important that you kind of grasp this thing, but it's a very similar concept to what we saw when we talked about how arbiters can be organized as a tree. Here we are organizing addition as a tree. Same thing happens with multiplication. And in fact, one of the key problems in CS theory that people have been addressing is how fast can I do a multiplication, right? I mean, normally when we multiply, we have 2 n-digit numbers, then we take n square additions, right? But could I do it faster? And how close can I, like, what's the fewest number of operations we can do? So that continues to be a research area. And and when you get into neural networks where we do lots and lots of multiplications as part of tensor operations, which is how neural networks represent their thing, this thing becomes even more important. And interestingly, this is kind of a few months ago, there was a result where the same outfit of Google, which created the AlphaGo system, which beat the world champion in Go, and likewise for chess and poker and things like that. Very similar strategy has come up with an algorithm for multiplying tensors, which beat the best algorithm that humans had come up with thus far. So we are already in a stage where in some cases now software is generating superior algorithms than what we are able to think of. Addition, on the other hand, we know how to do optimally, but multiplication remains open. Another thing oftentimes we face is, in many problems, neural networks is one, that oftentimes we have to do this kind of an operation. I want to add multiply some variable by some constant, and I do a lot of them and then add them up. This operation is called multiply accumulate, okay, MAC operation. So as you can see, it has lots of additions, right? I'm adding lots of CI, XI, but I'm also doing a lot of multiplication, except the multiplication here is interesting. CI is constant. It's not a variable, as opposed to doing something like this, where I'm multiplying 2 variables and then adding them up, right? So here is variable, here is constant variable. This actually leads to an interesting optimization opportunity, which is if you look at CI, right? Let's say constants are 32-bit, and let's say I'm multiplying my variables by lots of constants. Pretty soon, I can exhaust all possible positions where CI may take the value 1. So it turns out that for these kind of things, if you're doing a large number of these operations, you can do some additional clever optimization. Kind of much beyond the topic of this course, but it has received a lot of attention because nowadays we are interested in doing neural networks very efficiently, right? I mean, like you have like ChatGPT-4 by all accounts has number of parameters which are in like 1.5 trillion or something like that, right? So huge number of parameters. So every time you have an input going through these neural networks, you are doing like trillions of multiply accumulate operation in order to generate the next word in your stream. So while at this level, yeah, it's just an addition, but it's actually sitting in a loop where you are doing gazillion operations and have to do all of it in real time. So a lot of attention sort of goes into these things. Okay, so any questions before I move on? I kind of rushed through these things, but I'll have the TAs explain this thing more. But super important that sort of the main concept I want you to take away out here is the notion of propagate and generate. Generate refers to that whether a bit or a group of bit is generating a carry irrespective of the incoming carry. And propagate refers to that this bit or group of bit is going to propagate the carry which is coming in. Okay, it's not going to create a carry of 0. Okay, so that's the concept underlying kind of creating these bigger structures. If somewhere I know the carry is being generated, I don't have to wait for anything coming in. I can immediately kind of just say carry out is 1. And likewise, if I know that it's neither generating nor propagating, then I know that the carry out is 0. Okay, so that can also speed things up. No questions? Okay, let's move to negative numbers. So all of this we did thus far, it's all positive numbers, right? We are actually specifically positive integers expressed in base 2 positional notation. Okay, the adders we talked about will not work with one-hot coded numbers, for example. Let's say I give you 2 numbers which are one-hot coded, and I ask you to add them and give me a one-hot coded result. How would you do it? So 2 numbers, one-hot coded, add them, produce a one-hot coded number, and let's, for the sake of argument, assume that the result will fit into the same number of bits. Okay, so how would you approach that problem? Anyone wants to take a stab? I mean, remember, it's kind of like software. I'm giving you a library of modules thus far. You're raising your hand, so you want to try? Say it again. Encode them, add them, decode them. Yeah, absolutely. So using right. So if my number, we know how to add numbers written in positional notation, right? The standard base 2 notation. But I gave you one-hot coded. So now you think, oh, how do I go from one-hot code to standard compact representation? Well, that's a function of encoding. We have shown encoding, right? So you take one-hot numbers, use encoder, get number which is now coded, then use the adder that we just showed. Now output is again a coded number, and then you think, okay, how can I go from coded to a one-hot? And that's a decoder, right? So we apply a decoder. So you can compose things that we have seen in clever ways to kind of do it. You might want to think about, how do I want to do kind of representation of numbers, which are thermometer representation, right? So if you recall in thermometer, like if I give you 8 bits, you can represent 8 values, right? I mean, depending upon how many contiguous ones we are. Think about how might you add those, right? So, but again, using modules we have seen, you can compose them to do these kind of things. But we haven't seen negative numbers. How do we do negative numbers? There's no counterpart to one hot coding, obvious one. So how would you do negative numbers? Let's say I were to ask you, design me a system, design me a digital system which can handle negative numbers. What would you do?
Out of curiosity, why can't we use the adder for like
You're jumping ahead. We have not talked about two's complement. We will.
but for negative numbers, yeah, I would use this complement.
Sure. So you know, I don't know why you are in this class. You already know two's complement. So you can ignore the rest of the section. But ignoring his comment about two's complement, which I'm sure, I don't know, how many of you know two's complement? A big chunk. Okay. So this is what, CS33? Okay.
We actually learned it in this question.
Hmm?
It's from yesterday.
And in this question also, okay. So you have already seen two's complement, but I'll still go through it just to make sure that those who haven't, okay. So one way we can do negative numbers is potentially we can just say the positive number with a minus sign. So I kind of figure out some way of representing the minus sign. Unfortunately, that leads to complex hardware. So we'll see that there is a representation which is called two's complement, which allows us to use the same adder which we have designed, but for negative numbers too. So how does it work? So there are 3 common ways I can represent, or computers tend to represent negative integers while in binary. So one is called sign magnitude, which is what I just referred to, that I use some bits to represent the magnitude, that's a positive number, and 1 bit to represent sign. So I can say I have 32 bit, I'll use the bit number 31 to represent the sign and the remaining bits to represent the value. So it's called sign magnitude. 1's complement and 2's complement are a little bit less less direct to explain, so let's do it. So let's say I want to represent 23. Okay, so firstly, let's kind of back up a little bit, right? Let's say I want to represent all the numbers from minus 20, whatever, in some range, right? So if I have 8 bits to play with all those 8 bits, I can only represent 256 different things. So certainly I cannot no longer represent numbers all the way to 255, which I normally could, right? And normally with 8 bits, I can go from 0 to 255. But if I'm saying I also need to do negative numbers, then I have to sacrifice some positive numbers, right? So I can say, maybe I can go from minus 128 to 127, okay, some range, but I cannot represent more than 256 things. So going out here now, let's say I decide that I give you 6 bits. And the way I do this thing is, sign magnitude is that I use the lower 5 bits to represent the magnitude, and I use the most significant bit to represent the sign. Yeah. So most significant bit 1 means it's a negative number, it's minus, and 0 means it's positive, and the lower 5 bits give me the magnitude. What's the largest number I can represent with this sign magnitude? Largest in numerical value. Okay. Yeah, just this example, right? 6 bits. What's the largest number I can represent? To the 5th. To the 5th is 32. You can't represent 32 there. Huh? Someone said, right, what's the largest number will be positive, so 0, and then all 1, so that's 31. Okay, so plus 31. What's the smallest number I can represent? Minus 31, right? Most negative number. So do you see a problem with sign magnitude? Huh? There are two representations for 0, right? 1 followed by all zeros and 0 followed by all 0 are both 0 mathematically, and yet I have two representations, and that will complicate hardware, right? I mean, yeah, I can no longer do even things like equality very easily. Okay, so sign magnitude has a problem, but it's a scheme. One's complement. The idea in one's complement is that I first express the number magnitude of the number, and then I just flip the bits, and that would be the corresponding negative number. So positive 23 is 0, 1, 0, 1, 1, 1. Negative 23 is just inversion of that. Okay, so so that's one's complement. It's called one's complement because essentially what we are doing is we are subtracting from a number which is all ones. And whatever I get out here is the negative part. And I can do in the reverse direction also. So one way of thinking is we are flipping the bits, and the other way is we are subtracting it from all ones. So that's one's complement. The problem.
How does the computer know this is not 40 and it's minus 3? And this is eventually. Because it's also the representation 1 0 to 1 0.
Is a representation, right? But so this is where computer. Oh, there's no space. Okay, that's just a way for me to draw out here, just to. Okay. Oh, okay. So you are saying 1 0 1 0 0 0 is 2 4 8 16 32. 32 plus 8, 40, right? That's what your question is, right? Computer doesn't know. To computer is just bits. You will have to make sure that whatever the hardware the computer has, if you think of these bits as one's complement, then the computer should do something same. So computers will, so there are two ways of thinking about it, right? One is I can say I've designed a computer and it uses one's complement. And so whenever you give it 1 0 1 0 0 0, it will the adder, multiplier, subtractor, whatnot, they will be designed for an interpretation that is one's complement. Okay, and likewise for sign magnitude, it will look at the upper bits. What?
Oh, this is now assignment to watch.
No. Computers will handle only one of these. Not if. Yeah. So if I design a computer and say, this is a computer which uses one's complement arithmetic, then every time it will execute its add instruction, for example, it will interpret the two inputs as one's complement. Okay. If you want the computer to do something else, then you'll have to do it as part of your software. Okay. Now, the beauty of 2's complement is that the same adder, same multiplier, same subtractor can work either way. You don't even have to tell it. You can, if you give it 2 bits and you say, hey, these 2 bit patterns, I am thinking of it as an n-bit positive binary number, the adder will outputs bits, which will be a valid result. And same adder and same bit pattern, and I say, oh, no, I was wrong. I'm thinking of it as a 2's complement sign number, which I will tell you shortly. The adder will output the same bit pattern, except that that will be a valid representation in 2's complement. So 2's complement has a special property that you can interpret whichever way, same hardware works. And you don't even have to tell what to do. 1's complement and sign magnitude do not have that property. And therefore, in 1's complement and 2's sign magnitude, if you were to suddenly say, hey, I don't want to do signed arithmetic, I want to do unsigned arithmetic, you'll have to do some you'll have to do some special games there. So 1's complement suffers from the same issue of 0 having 2 representation. all zeros and one followed by all zero are both zero. And so, so that's a problem. So one's complement, just flipping things. Okay. Now, if we think about it, I give you n bits, it can represent 2 to the power n things. That's an even number. If I'm trying to represent negative and positive numbers, and if one of those things has to be zero, then I'm left with odd choices, right? I mean, if I have 2 to the power n things, one of which represents zero, then left over is an odd number of things. That means I can never, if I want a unique representation for zero, then I have to either have more positive numbers or more negative numbers. I cannot have symmetric system. I cannot go from minus k to plus k, right? Because if I go from minus k to plus k, then I need two times k plus one things. That's odd, and therefore, right? So I can eat. So if I have n bits and I want to fully use all the bits, all the combinations, then I have to inevitably live with this reality that either I will have one more positive number or one more negative number, okay, around zero. So 2's complement does that. Okay, it goes from, like, if you have an 8-bit thing, then 2's complement will go from minus 128 to plus 127. Okay, so how does 2's complement work? 2's complement works by the following. It does the same thing as 1's complement, but after doing the 1's complement, it adds 1 to it. So plus 23 is the same, right, in all schemes. I take this 0, 1, 0, 1, 1, 1. I do the 1's complement, 1, 0, 1, 0, 0, 0, and then I add 1 to it. So I get 1, 0, 1, 0, 0, 1, and that's what you have out here. So it flips and adds 1. There are other ways of doing this conversion, but that's the one which is easiest to think of. Okay, so let's dive more into it. Okay, so sign magnitude, highest bit is sign, the rest is magnitude, and we have already talked about it. Main thing is, if I give you n bits and I say we are using sign magnitude, then I can represent numbers in the following range, with this way, because 1 bit is eaten up by the sign, and then we are going symmetric around it. Sign magnitude used to be used in computers at the hardware level, but and you probably can still find some custom chips and all which do that, but there is, generally speaking, sign magnitude is something that you deal with at the human level, right? We write minus 23 or plus, right? But not at the hardware level. 1's complement, again, in all these schemes, if you look at the highest bit, if it is 1, it's a negative number. So 1's complement, same story. The negative it's basically we subtract the number from all 1's to get its complement. It's essentially flipping the bits, and that's what 1's complement does. So what's the range of representation with this? The most negative number here versus the most positive number. So most positive number is 0 followed by all 1's, and most negative number would be the inversion of that. So it would be what? What do you think would be the most negative number in 1's complement with 6 bits? One followed by? One followed by all 1's. So let's see. So 0 followed by, this is the most positive number. If I take its 1's complement, it's 1's followed by all 0's. Okay, so that would be the most negative number. So range of representation is going to be, this is the most positive number, 2 to the power n minus 1 minus 1. This n minus 1 is because we have 1 bit is going away to sign. And then as usual, we get the magnitude, and this is a negative of that. So that's the range. And there are two different bit patterns, both of which will correspond to 0. So that's 1's complement. Okay, 2's complement. So 2's complement is what is used, and we'll see shortly what the reason behind it is. Okay, even though it has it no longer will suffer from this problem of 0 having 2 representations. Okay, and by the way, it also ends up having this nice property that the same, if I give you an n bit n bit triple carry adder, you can either use it to add n bit positive numbers, or you can use it to add n bit 2's complement numbers. Same hardware works. You don't even have to tell it. You don't even have to tell, hey, you are now adding positive numbers, or hey, you are now adding 2's complement numbers. It just works, and that's the nice part. So so basically, kind of the idea is that we positive numbers are represented with a 0 followed by their magnitude. So that's as it is. For negative number, we take the 1's complement and then we add 1 back to it. Okay, so if you think about it, what is 1 1 1 1 1 1? All ones, right? If you think about it, we are subtracting from that, right? So we are doing this minus x, where x is the positive number, and then we are adding back 1 to it. Now, if you think about it, this 1 1, I can add these two things together. So what I really have is a following. That's what I'm doing, right? I mean, I'm kind of subtracting x from 1 followed by 6 zeros, whatever that positive number is. And that's what's going on. 2 to the power n is really a 1 in followed by these zeros. So minus x is really equivalent to this. Okay, that is, if I give you the bit representation for bit representation for x, then minus x is the bit representation we get when we do 2 to the power n minus x in our normal arithmetic. So let's see if it works out. This is 23. What is this number? Well, 2 to the power this is, let me make sure I don't screw up. Okay, so I already screwed up. This is 1 2 3. There's another 0 here. Okay, so I have 1 followed by 6 zeros. If I were to look at that number, okay, as a positive number, and then I subtract 23 from that. So that's what we will do. Let's see. Okay, no, we don't have it. Okay, so this number, what is the, if I were to just say 1 followed by 6 zeros, what number is that in positive terms? Just thinking of it as a base 2 number. So it's 0 1 2 3 4 5 6. So it's 2 to the power 6, right? That's where its weight is. What is 2 to the power 6? Well, that's 64. I hope I don't make a mistake. Yeah, 64. I do 64 minus 23. I end up with 41. And this number, if I were to think of it as a positive normal base 2 number, is 41. So what's really going on in for 2's complement is that I'm kind of switching back and forth between thinking of it as 2's complement and thinking of the same bit pattern as a base 2 number. So I start with 2's complement representation of 23. I then switch gears. I say, let's subtract 23 from the 7-bit number, which is 1 followed by all zeros. That corresponds to 64, or in other words, correspond to 2 to the power n. And then I subtract x from it. Whatever bit pattern I get is the bit pattern out here. And that's how kind of the math works out. So so the bit pattern corresponding to minus x can be obtained in this particular manner. In other words, minus x, if I think of that bit pattern, and if I say, let's treat that bit pattern as a positive number, then its value in that system is 2 to the power n minus x. So same bit pattern, I can either think of it as minus x 2's complement, or I can think of it as 2 to the power n minus x in our regular base 2 system. Okay, so same bit pattern. Bits. Yes. So in our case, n is 6.
Okay, so then why are there 7 bits?
Because when we are let's start with like the original definition of 2's complement, right? We flip and add 1. Flipping can be viewed as 1 1 1 1 1 1 6 bits minus whatever is the bit pattern, right? And then we add 1 to it, so it's basically all ones, 6 ones minus x plus 1. That's what the recipe for 2's complement is. But what I'm saying is, imagine I first add these and then subtract x, right? So, but now if I'm adding all ones plus 1, then I need 1 more bit because there'll be a carry out. So that's why I have 7 bits, 1 followed by 6 zeros. Okay, and that value is 2 to the power n. Okay, and so here what the game that's going on is same bit pattern, right? 1 0 1 0 0 1 is representing minus 23 in 2's complement, or alternatively, it's representing, in our particular case, 2 to the power 6, because there are 6 bits, minus 23 in base 2 arithmetic, normal base 2, thinking everything positive. So same hardware which we previously designed, it doesn't care, bits are bits, and but this observation, soon you will see, lets us sort of use the same hardware. You don't have to design a special 2's complement adder, subtractor and all. You can use it to add n-bit positive numbers or n-bit 2's complement numbers. So is there a negative 0 out there? So here things get interesting. 0 is all zeros. What's the 2's complement of 0? Well, all zeros become all ones, and then we add 1, we get back all zeros. So if we apply a recipe to 0, I get back the same bit pattern, all zeros. So 2's complement does not suffer from the problem that 0 has 2 different representation. I take plus 0 and then I attempt to compute minus 0, I get back the same bit pattern. So there is no negative 0. Or in other words, positive 0, negative 0, they're both all zeros. So that gets rid of our problem. So then question becomes, what's the highest number in this? Well, what's the highest number? It's going to be 0 followed by all ones. So in our example, 0 followed by 5 ones, so it's still going to be plus 31. Right? So the highest number here in this thing would be 0 1 1 1 1 1, which is equal to 31. What's minus 31? What would it look like? Anyone wants to take a shot? So one 0 0 0 0, but remember we have to add back 1 to it. After flipping, we add 1, so it would be 1 0 0 0 1. That would be minus 31. Okay, or equivalently, right? I mean, so there are 2 ways to get to 2's complement. One is flip and add 1. Okay, so I started with this, I flip, so I get 1 followed by 5 zeros, and then I add back 1, so this becomes 1, right? So 1 0 0 0 1, that's minus 31. So I can do it that way. Or alternatively, I say, let's subtract 31 from 64, right? 2 to the power 7 minus 31. 2 to the power 7, sorry, is that what I had? I just want to make sure. Sorry, 2 to the power 6. So I subtract 31 from 64, that is 33. And if I am right, this number is 33, interpreted as a positive binary number. So I can do it whichever way I want. I can either say flip and add 1, or I can say think of it temporarily, think of it as if I'm doing regular base 2 arithmetic, subtract it from 64. So that works. What do you think this number represents? Or sticking to our 6 bits, let's say I give you 111 111, all ones. What number does it represent? What is its value? Huh? -1. So how do we know it's -1? Well, we know it's a negative number. So let's take its complement, right? So it would be all zeros, add back 1, all 0 1. So corresponding positive number is 1, and therefore it's -1. Or in an 8-bit notation, this is minus. So if I give you, so let's try something out. Actually, temporarily, I'm going to stop sharing. Okay. So this is a little bit of C code out here, and I just want, so int x, and let's run this thing, and I'm going to explain this thing. Okay. So firstly, okay, so let's walk through this thing. I declared a variable x, which is just a regular int. It's running on some computer on the cloud. I first print how many bytes this number has, and you see that it says it has 4 bytes. So it's a 32-bit number. So it's probably 32-bit int, 32 bits, right? Then what I do is I say, let's make x equal to -1. Okay. And then the game I play is I take the address of x, I cast it to, I say, think of it as an unsigned int star, and then take its value. So what this trick does is it prints out the bits that make it up, and you see that it's printing out all f's. That means -1 in the computer, and if you count, there are like 8 f's out there. So what it's saying is -1 is 8 f's, all 1, 32 bits of 1. So that's -1, which is what kind of I was explaining for our particular example. Let's try something else. Actually, okay, so what I have put out here is 0x8 followed by 7 zeros. So it's a number where there's a 1 followed by all 0, right? 8 is 100, and then everything else is 0. So it's a 32-bit number where the first bit is 1 and everything else is 0. Now let's think about it. What value does it correspond to, right? I mean, it's a negative number. And if I take its 2's complement, it would be 0 followed by all ones, right? And then I add back 1 to it. So it will become the same number, right? 0x800. So its value is whatever is a 32-bit value of the what's the normal value of 1 followed by all zeros. So you'll see it's going to be a very large negative number. Okay, so let's run it. Yeah, I didn't print. Okay, so see it printed x equal to -2147886. Trust me, but it corresponds to the number 2 to the power, corresponds to the number where I have 1 followed by 31 zeros. So one thing if you notice is that if I have 1 followed by a bunch of zeros, if I take its 2's complement, I get back the same thing. So what you see out here is that there are 2 numbers whose 2's complement is the same thing. All zeros result in all zeros, and 1 followed by all zeros result in the same number. What it also means is that on our computer, I cannot represent this number in a positive manner. It won't fit. And this is why, so the maximum positive number that I can put into a computer like this is going to be 0 followed by all ones. And that number would be all this number, but with the 7 out here. And let's try that out. So let's say I say, what's the let's see. 1, 2, 3, 4, 5, 6, 7, 7. Okay. So most positive number has one smaller magnitude than the most negative number. And this is where 2's complements asymmetry comes into play. It can represent, like if the highest number it can represent is x, then the most negative number it can represent is minus x plus 1. And okay, so that's the characteristic of 2's complement, that it has this asymmetry in it, and we'll see shortly how it plays out. But okay, so let's go back. So this number, let's imagine I have an 8-bit system. All ones, that's 255 in its binary value. It's a negative number, and it corresponds to -1. As you can check by flipping it. So if I have, let's say I give you an 8-bit computer, then you would see that in the 8-bit computer, as I go from all zeros to all ones, my numbers progress from 0 to 127. So that's 0 followed by all ones. If I add 1 to it, thinking of it as a base 2 number, 0 followed by all ones is 1 followed by all zeros, if I were to think of a base 2 number. But in in terms of its 2's complement interpretation, it's going to be minus 128. So you can try this thing out. In my example, I've shown you the most positive number integer. If I add 1 to the most positive integer, then within the computer, it doesn't remember. Computer just think of it as a bit. And when you add 1 to it, it's just going to happily add 1 to it. But what you will see is when you try to print it out, you will get a negative number. Okay, and let's try that for a moment, just to convince you that that's what happens. So here, as you can see, if I had 0 followed by all ones, I added 1 to it, I'll get 1 followed by all zeros. But in its 2's complement interpretation, it will go from 127 to minus 128, from most positive number to the most negative number. Okay, it kind of rolls over. And then it will reduce, and by the time we are at all ones, here it's minus 1. But let's see on our real computer, does the same thing work? Okay, so again, I'm going to stop share out here, and actually I keep forgetting to share here. So let's see. So let's go back out here, and what I'm going to do is, so remember at this point, this is most negative. This is most positive. Now let's do x equal to x plus 1. And just to convince you that our computer is incapable of adding positive 1 more to it because it can't represent it. Okay, so if I were to print it out, one sec. See, so most positive was this, but I added 1 to it. I actually suddenly got the most negative number. So this is called overflow, because once I hit the most positive, adding 1 to it, because x is declared here to be just a regular int, signed integer. So it's, when I say print, it's saying, let me think of the bits in x as a 2's complement number. And that turns out to be the number which is 1 followed by all zeros, which is the most negative number. So overflow can happen on your computer, okay? Because we have a finite range. But the funny thing is, like I said, most positive will go back to the most negative, and the reverse also works, right? I mean, if I take the most negative and subtract 1 from it, then I'll certainly get the most positive number. Now, as you can imagine, this can create chaos in your software if you're not careful about it, right? I mean, if you are using signed integer and you are merrily happily adding, subtracting and all, and you don't keep track of what the computer is capable of, you will have underflow, or or overflow. Interestingly, the computer didn't complain, right? I mean, you would say, hey, why can't I not, why shouldn't I design my hardware so that if I attempt to add +1 to the most positive number, then it should barf, throw an error or something like that? It can't, because the hardware doesn't know that those bits, you are treating them as 2's complement, or whether you are treating them as regular positive binary number. Hardware thinks of them just as bits. And it's actually just doing the normal addition function that we described, the ripple carry. It doesn't know which way you are going to interpret it. So it can't and shouldn't do that, right? I mean, you have to keep track of it. And this is a job of, like, if you are worried about this happening, then you should always check that before adding, I mean, ideally, if before adding 1, you should check you are not already sitting at the most positive number, but there is an easier way of checking it. So how, let's say I have the variable x, I do x plus 1, and I'm worried that did an overflow happen? Can you think of an easy way in software to check that an overflow happened? So I had x, I said y equal to x plus 1, and I want to quickly check that I was not in this kind of situation where x was already too high, already the maximum number. And more generally, let's say I have two int, x and y, and I say z equal to x plus y, and I'm worried that an overflow may have happened. So can you think of some easy way of checking? You could do something like that, but let's say we are in the world of software.
If the result is less than
Yeah, or you could say if x was positive and y is negative, I'm in trouble, right? So I'm doing addition, x plus 1. If x is positive, then okay. And likewise, if I'm doing x minus 1 and y equal to x minus 1, and if x is negative and y is suddenly positive, I'm in trouble, right? I mean, so these are the easy checks, and you can now think of hardware can pull off something like that too, right? Hardware can check that, oh, I was adding two positive numbers and then suddenly the output is negative. There's something wrong, okay, or vice versa. So let's go back to the slides. I hope this going back and forth is not messing up the recording, but okay. So the way to think about 2's complement numbers then is that they kind of form a cycle, okay? I start with 0, and the bit patterns here are as if they were regular base 2 numbers, except the interpretation is I go 0, 1, 2, 3, all the way to the most positive number, and then suddenly I go to the most negative number, which is out here. So from +7, I went to -8, and then count down all the way back to 0, okay? Now, how should the software think of it? How should the hardware think about it, right? I mean, we need a cleaner abstraction. So I have n bits, and it's typically 32 or 64 on a regular computer. What I want to do is sorry about it. Okay. So most positive number in n bits will have the upper bit 0. So bn minus 1 is going to be 0. And the lower bits, whatever is their value, is the value of my number. So I can say if the number is positive, then the value of the number is this, except that I only take into account the lower n minus 1 bits. If on the other hand, the number is negative, then the uppermost bit is going to be 1. And in that case, you can check out the value is going to be this, which is I first take the negative of the number and subtract the number, and then I take a negative. You pull all of this together, and you can think of 2's complement number in these terms, that the value of a 2's complement number is given by this formula. It is uppermost bit has the weight -2 to the power n minus 1. So if I'm looking at 32-bit numbers, uppermost bit has a weight -2 to the power 31 now. And the lower 31 bits, we treat them as normal. So if highest bit is 0, this term will disappear, and we will just have the standard thing. If on the other hand, highest bit is 1, then we'll end up with a negative number. So you can think of 2's complement as a funny kind of positional system where bits 0, 1, 2 through n minus 2 have their standard weights 2 to the power I. But the most significant bit has a weight which is negative. It's to the power n minus 1 instead of just positive to the power n minus 1. And if you think of it like this kind of a number system where first n minus 1 bits have positive weights and the most significant bit has a negative weight, then you get the right values and things kind of add up. So there are a variety of ways of thinking about this. Let's see, how are we doing in time? We have a couple of more minutes. So at a manual level, I already talked about two ways you can find, like given a 2's complement number, what take it 2's complement, so you can find its negative. I can use this formula. 2's complement of x is this. Yeah, so that kind of works out. We could approach 2. We can take 1's complement and add 1 to it. We also saw that, and we showed that the two are equivalent. So I could do that, and you can actually make hardware. If you think about it, like how can I, if I give you a if I want to create a hardware to do it, I could sort of do it this particular way, or the first way as a subtractor. I could do that. There is an approach 3, which kind of for manual purposes works the best. And the idea is the following. Let's say I give you a number. You start from LSB. And then as long as the number is 0, the digits are 0, you keep copying them. And then moment you reach a 1, you copy that. And after that, you flip the bits. So let's see if that works out. So let's say I have this number. And I want to take its 2's complement. In other words, I want to find what the negation of this number is. So what I do is I start from the right. So I copy 0, 0 through the first 1. And then I flip everything after that. So the blue part is flipped, the red part is copied. Now this is great for manual thing. It's not how you would do on a computer. On a computer, like for hardware design, one of the first two approaches is a superior one. So practice a little bit on sort of become comfortable on how to go back and forth and all. Almost all computers natively at the hardware level use 2's complement, just because there is no difference between 2's complement, like same hardware works for n-bit positive numbers or n-bit 2's complement number. It's just how we humans interpret it. So you can try out some of these examples, and let's see. Yeah, we are at time, so we're going to pick this thing up on Monday. But yeah.
I have a quick question.
Sure.
So if I have an n1 bit input combinational logic circuit that has m1 bit outputs, how many possible systems can I have with that configuration? Like, what's the expression?
You are asking the homework problem.
Well, not necessarily, but the
I want you to think.
What's the expression for such a?
I don't know. You'll have to figure it out. But we did cover this thing conceptually in the class. I'm not going to give you the expression. You just reason your way through. This is combination type problem from.
Is that an multiplication at the day of the possible inputs and outputs? Or is it
Let's think about it, right? I mean, how many different ways something can happen? This is a problem.
Are you asking for the number of mappings, or are you asking for something else?
I'm asking for in that particular problem that if I think of all possible functions of that type, how many functions are there, right? I mean, each set is it's a set of all possible such functions, right? I mean, so how many distinct functions that exist? Like, for example, if I say how many distinct functions exist which have one input and one output, how many are there? Two, right? Identity and not. How many distinct functions are there with two input? We had that in the class. Two input and one output. Yeah, we did in the lecture, right?